This is Unit 2 in chemistry class, and this is the second video entitled Numbers in Science. This PowerPoint is also available that you can print it out and then be taking notes as you follow along the video. And I'll tell you what you should be writing down as we go. So, numbers in science. Let's use them the right way. There are two kinds of numbers in science. There are exact numbers. We know their value exactly. And then there are inexact numbers, and those are values that have uncertainty. Let's talk about exact numbers. They're defined values. When we say there are 12 eggs in a dozen, there are exactly 12 eggs in a dozen. Sometimes definitions like 1,000 grams in a kilogram, those are exact numbers. Whenever we count, like there are 24 students in our class, those are exact numbers. Inexact numbers are numbers and values that have some uncertainty and some error in them. All measurements that we make in science are inexact numbers with error in them. This error can come from the equipment that we're using if it's not calibrated the right way, or it could just be human error. We can all interpret the markings on a ruler or on a burette differently. Now we've got to get some vocabulary words that we use in science when we're talking about numbers. And the first one is uncertainty. And this is how we express how sure we are that the measurement is truly what we say it is. Uncertainty is usually expressed with a plus or minus notation. So for example, if I measure the length of a line segment and I found it to be 1.58 centimeters, I could express my uncertainty plus or minus 0.01 centimeters. Generally, the last digit reported in a measurement has some uncertainty. Accuracy. It is the correctness of a single measurement. Now, what do I mean by that? Well, you compare your measurement to a true or a scientifically accepted value. Accuracy. How close is your measurement to what the true value actually is? And this is different from precision. Precision refers to how well experimental values agree with one another. I like to think of precision as consistency or reproducibility. Generally, the more decimal places that agree, the more precise you are. So let's look at an example of precision. If we had a balance in the lab that could measure a mass to 1/10 of a gram, we weigh the raisin the first time and it's 1.2 grams. And we weigh it again and it's 1.2 grams. If we have an analytical balance that now goes out 3 decimal places to the thousandth place, well, the first time we weigh it, we might get 1.234, and the second time 1.235. Which balance has the greatest precision? And the answer is the analytical balance, because we are getting measurements all the way out to the thousandth decimal place. Now, precision comes at a cost. The analytical balance is a lot more expensive to buy than the other balance shown here. This is a really common analogy for trying to understand and remember accuracy and precision, and it's a dartboard. The bullseye would represent the true value or the accepted value. Well, the first dartboard on the left, so part A, has low accuracy. They never hit the bullseye. It also shows low precision because the darts aren't anywhere near one another on the dartboard. So dartboard A has low accuracy and low precision. Now, dartboard B, the second one over from the left, that one doesn't have, it has a very low accuracy. No darts went in the bullseye. But it's very precise. All the darts agree with one another. They're in the same region on the dartboard. So dartboard B has low accuracy, no bullseye, but high precision. Well, dartboard C, which is the third one over, well, it has pretty high accuracy. Those darts are all pretty close to the true value, the bullseye, but it has low precision. Those darts aren't close to one another. And the final dartboard, the one on the far right, D, high accuracy, hitting the bullseye every time, and high precision because the darts are agreeing with one another. They're all in the same region of the dartboard. Well, we need to talk about something called significant figures. Some teachers might call them significant digits. From now on, I'm going to call them sig figs. So sig figs are significant figures. Well, what are they? They're all the digits in a measurement that you are sure of, plus one digit that you estimate. Sig figs are a way that we can express our precision. The more sig figs we have, the more precise the measurement. Well, let's learn how to count sig figs. Here's our first number, 1.85040. Well, we're going to count from left to right. We always start counting at the first non-zero digit. So we're going to start counting with the digit 1. If there's a decimal point written, you count all the digits after the decimal point. So let's go ahead. There's a decimal point in this top number. We are going to count all the digits. So the 1, the 8, the 5, this 0, this 4, and that trailing 0. Every single digit is significant. There would be 6 significant figures in that number. If you have this PowerPoint printed out, write a 6 in that blank. Now, what do we do if there's no decimal point written? Well, if there's no decimal point written, we are not going to count the trailing 0 at the end. So let's look at this number here, 1.85040. We start counting from left to right. The 1 is significant, the 8, the 5. This is not a trailing 0. I like to call it a sandwich 0 because it's stuck between two digits. So we are always going to count a sandwich 0. The 4, we will count that, but this trailing 0, we will not count. Above, we counted the trailing 0 because there was a decimal present. In this number below, there's no decimal present. We will not count that trailing 0 as being significant. So in your notes, let's count our sig figs. 1, 2, 3, 4, 5. There are only 5 significant figures in that number. Let's practice some more. How many sig figs in the following number? Well, this 0 is just to hold the decimal place, 0.009. We don't count any leading zeros. We never do. They just hold the decimal place. So this first value, 0.009, would have one significant digit. Don't count zeros at the beginning of a number. Let's look at the second example, 0.00900. We're not going to count these leading zeros. We'll start counting at the 9. But what about the trailing zeros? We count them when a decimal is present. There's a decimal. We are going to count the trailing zeros. So this number, 0.00900, has 3 significant figures. So you should write that down. Again, not significant, not significant, not significant. We start counting significant, significant, significant. These trailing zeros are significant Because there's a decimal and they are after that decimal place, after a digit. Well, 114,000. 1, 2, 3. Trailing zeros. No decimal is present. That number would have 3 significant figures. We won't count the trailing zeros. Now, what if those trailing zeros really were significant? How could we let people know that those zeros were really significant? What you can do, it looks kind of funny, but you can put a decimal. So here, because these are trailing zeros and a decimal is present, we're going to count them. So our last example, 114,000, there's a decimal present. We will count those zeros after those digits. So there are 6 significant digits in that value. So I hope you've written this down. 1 sig fig here, 3 here, 3 here, and 6 here because of the presence of the decimal. Let's just summarize. All non-zero digits are significant. Zeros in the front never, ever count. They're just holding the decimal place. Zeros at the end of a number, which I call trailing zeros, you count them only if a decimal point is written down. All right, now measurements, calculations, sig figs. Let's try to use those 3 words in a sentence. The least precise measurement limits the certainty of the calculated quantity and determines the number of sig figs in the final answer. So again, we are going to have to look at our measurements, and then when we use measurements and calculations, we're going to have to figure out how many significant figures to report in our answer. Remember, calculators do not know about significant figures. Okay, this is the end of the first video, and we're going to have one more that you need to watch that goes along with this PowerPoint. So stay tuned and click on the next video.